we only need to look for the first point of differentiation. It is not the overall coolness of the group. Welcome, OChemNinjas. Assigning the label to an R or S stereocenter can be a historically confusing concept for students. There are 4 important tasks you must complete. 1, you have to find the stereocenters in a molecule. 2, you have to prioritize the 4 groups around that stereocenter. Number 3, you have to make sure the number 4 group is pointed to the back. Number 4, you have to assign the clockwise or counterclockwise circle to assign it R or S. This video is only going to cover number 1 and number 2. We're going to find the stereocenters in a molecule and learn how to prioritize the 4 groups around that stereocenter. We are not going to go through the process of actually assigning R or S. There are lots of tips, tricks, methods, hand techniques that you can use to assign R and S, and I've got an entire playlist on all of those techniques that I'll link to down below. This video will give you the skills you almost need to take for granted in order to do those later tasks of assigning R and S stereocenters. Let's get started. The first thing we need to do is find all of the stereocenters in a molecule. Carbon number 4 is attached to bromine, oxygen, carbon number 3 chain, and a hydrogen. That is 4 unique groups. This carbon, number 4, is a stereocenter. This is our first stereocenter in the molecule. Now that we've identified the stereocenter, we can apply the priority labels to the 4 groups around that carbon. To do that, we follow a process called the CIP Rules. The CIP Rules are an acronym that stand for Cahn-Ingold-Prelog, the 3 chemists that devised these rules. And it's okay to say that this is a human construct. It means nothing chemically. It means nothing physically. It means nothing in terms of physical properties or boiling point or hydrogen bonding. It's just a human construct to prioritize the 4 groups around a carbon so that we can assign it also a human construct, an R or S label. So if the rules seem kind of arbitrary, they are. We certainly could have come up with other rules, but we chose the CIP rules, and this is the one we're going with. To apply the CIP rules, what I would recommend is drawing an abstraction of the stereogenic carbon down below. We're going to prioritize these 4 groups, priority number 1 down to priority number 4. At that point, only the priority number matters. It won't matter if it's a bromine or an oxygen or a carbon. All we're going to do is put the numbers 1 through 4 around this abstraction. That's all that's going to matter in the end. That allows us to do our messy work off to the side and keep the original structure clean so we can go back and look at it later. It's very easy to start cluttering up your original structure with all sorts of labels and numbers and arrows, and then you can't really see what's going on. I would highly recommend abstracting your work off to the side. All right, so finally, what are the CIP rules? We look at the stereogenic carbon and we compare the 4 elements immediately attached to that stereogenic carbon. Every word there was very important. We are looking only at the 4 atoms, not the whole groups. The 4 atoms immediately attached to that stereogenic carbon. Again, I would recommend abstracting that off to the side. I like this table setup. It keeps things nice and organized. So the first thing we need to do is find the 4 atoms immediately attached to the stereogenic carbon. For carbon number 4, the 4 elements immediately attached to carbon number 4 are carbon number 3. I would recommend including the carbon number label, the bromine on the dash, the oxygen, and the implied hydrogen on the wedge. These are the 4 elements immediately attached to carbon number 4. I'm not looking at the whole group, just the immediate element attached to our stereogenic carbon. From here, I'm looking to see if any of these elements are listed only once. If they are, then I can prioritize them. In this case, all 4 of these elements are unique, so we can go ahead and give our priority labels right away. According to the CIP rules, once we find a point of differentiation between the elements, we can assign the priorities based on atomic number and atomic number only. The larger the atomic number, the higher the priority. Why atomic number? Why not electronegativity or size or something else? I don't know. It's a human construct. We could have picked whatever we want. Atomic number is easy to find on the periodic table. Based on that, the bromine is going to be priority number 1 because it has the highest atomic number. Oxygen will be priority number 2, followed by carbon, and followed by hydrogen as priority number 4. Pro tip, if there's a hydrogen, it will always be priority number 4. Hydrogen has an atomic number of 1. Now that we have the priority numbers, we can put those priority numbers on the abstracted version that we drew previously. Number 1 priority is the bromine, which was on the dash. Number 2 priority was the oxygen, which was in the plane. Number 3 priority was the carbon, which was also in the plane. And the number 4 priority was the hydrogen, which was implied to be on the wedge. And that's all we need to do to apply the CIP rules to prioritize these 4 groups. We can now take this abstraction and rotate it to get number 4 on the dash if we need to, or use one of our other tricks to assign it ultimately R or S. That's not the subject of this video. Although if you want to play along at home, this is an S stereocenter. I would put it in all 3 places in our abstraction, on our table, and in the original molecule so your instructor knows where to find it. We got a little lucky here that all 4 of the elements immediately attached to the stereocenter were themselves unique. Had any of these tied and been the same element, we would have had to do further analysis that we'll look at in the next example. To look at what happens when groups tie, let's go back to a fairly straightforward example. First, we need to find the stereocenters. Carbon number 2 is attached to the oxygen. Carbon number 1, which is a 1-carbon chain. Carbon number 3, which is a 2-carbon chain, so they are unique. And a hydrogen, which is also unique. So yes, this is attached to 4 unique groups. Carbon number 2 is a stereocenter. Now we're ready to apply the CIP rules and prioritize the groups. I've abstracted the stereocenter down below, and I've got my table ready to go. The 4 individual elements attached to carbon number 2, we have the oxygen on a wedge. we have carbon number 1 off to the left, we have carbon number 3 off to the right, and we have the implied hydrogen on the dash as their fourth group. If any of these are unique, we can go ahead and assign their priority number. Oxygen and hydrogen appear in this list only once, so we can go ahead and prioritize them. Of this list, oxygen has the highest atomic number, so it will be priority number 1, and hydrogen will always be priority number 4 if it's present. But what about carbon 1 and carbon 3? Those are the same element. They tie. How do we handle it if the elements tie? The rules for what happens when we tie are kind of like the kids' card game War or Battle. Did you ever play that as a kid? Two people would have a stack of cards and they'd flip over a card, and the highest card would win the battle and win both of those cards. But if you flipped over 2 cards and they tied, that was a war. Do you remember what happened when that would happen when you played that game as a kid? If the 2 battling cards tied, you would put down 3 cards face down that you couldn't see, and then you would flip over a last card, and whoever won that battle won all the cards on the table, 10 cards in total. Very exciting. We do something very similar here when 2 of our elements tie when we're trying to assign priority. Here we have carbon 1 and carbon 3 that are both the same element, so we compare the next 3 groups bonded to the tying elements, just like we would in war. We move our focus over to carbon number 1, and we look at the 3 elements immediately attached to carbon number 1, never going backwards back to carbon number 2. And we write those 3 elements in priority order next to carbon number 1. It's very important to write them in priority order. So the 3 elements immediately attached to carbon number 1 are all 3 hydrogens. We list them in priority order. Since they're all hydrogens, we list all 3 of the hydrogens in a row. The 3 elements immediately attached to carbon number 3 are 2 implied hydrogens and carbon number 4. So we list those in priority order. So we would start with carbon number 4 and then the 2 remaining hydrogens. From here, we look for the first point of differentiation, and that is our tiebreaker. It's very important we look for the first point of differentiation. That's why it's so important to write these groups in priority order. In this war, the first point of differentiation is right here at the beginning, hydrogen versus carbon. Carbon is a higher atomic number than hydrogen, so carbon number 3 is ultimately going to be our higher priority group over carbon number 1. Neither of them are higher priority than the oxygen, so carbon number 3 is priority 2, and carbon number 1 is priority 3. Let me go ahead and just kind of disabuse you of any tips or tricks you think you might see now. The longer chain is not necessarily always the higher priority. It's the first point of differentiation. That's why it's important to go through this analysis as long as you need to until you get to the first point of differentiation. Now that we have the 4 groups prioritized, we can add those priority labels to our abstracted element over here. Oxygen is number 1 priority, it'll be on the wedge. Carbon number 3 is 2 priority, it will be off to the right. Carbon number 1 is 3 priority, it will be off to the left, and our implied hydrogen on the dash will be number 4 priority. Again, it's not the point of this video, but this is an R stereocenter, and I would write it in all 3 places so that your instructor knows where to find it. Let's finish out this video with a few examples to explore some of the nuances of some of these rules. Take a second, pause the video, see if you can assign the priorities to the stereocenters in this molecule. This molecule only has 1 stereocenter, carbon number 2. I've abstracted it over here. Here, the end of plane bonds go up to the right and to the left. We need to reflect that. And I've got my table set up and ready to go. The 3 groups attached to carbon number 2 is carbon number 1, carbon number 3, carbon on the dash, and the implied hydrogen. Hydrogen is the only unique element in this group, and it's always the lowest priority, so we can go ahead and say that hydrogen will be priority number 4. Here, we have a tie between 3 elements, no big deal. We'll still play war. We'll still go out to the next 3 elements attached to each of these 3 atoms and see how they compare. Remember, it's the first point of differentiation, not the overall coolness of the group, so don't make any judgments based about what you see in the molecule before you do the analysis. The next 3 elements immediately attached to carbon number 1, not going backwards, are chlorine, hydrogen, and hydrogen. We put those in priority order. Chlorine will come first, followed by the 2 hydrogens. The next 3 elements attached to carbon number 3, what do we do with this double bond? Don't get too worked up over multiple bonds. We see them all the time in the CIP rules. Carbon number 3 is bonded to carbon number 4 twice, so we would include it twice in our analysis. So it's bonded to carbon number 4 twice and an implied hydrogen. So carbon number 3 is attached to carbon number 4 again in the double bond, and the implied hydrogen. Finally, carbon on the dash is a methyl group attached to 3 hydrogens, so we put those 3 groups on our list as well. Now we're ready to look for our first point of differentiation. Here, it happens to be here. That first element in the list is different for all 3 of these groups. That's why it's important to list these in priority order. Chlorine has the highest atomic number, so it will be the highest priority. Carbon is next, so it will be priority number 2, and hydrogen is last, so it will be priority number 3, followed by our implied hydrogen, number 4, as the lowest overall priority. Now we're ready to add these to our abstraction. The carbon number 1 group is priority number 1, it will go up to the top left. The carbon number 3 group is second priority, it will go to the top right. The dash methyl will be priority number 3, and the implied hydrogen will be priority number 4. How did you do? Did you get these priority labels? And if you want to double check yourself, this is an S stereocenter. Notice what happened here. The shorter group with the chlorine ended up being the higher priority group over this much longer group with the double bond and the T-butyl group. The overall coolness of the group did not matter. It was the first point of differentiation. That's why it's important to abstract this out and do the analysis one step at a time. Cyclic molecules are not treated any different than acyclic molecules, so go ahead, pause the video, see if you can find all the stereocenters in this molecule and apply their priority labels to those groups. This molecule only has the one stereocenter. Carbon number 2 is not a stereocenter because it has 2 identical methyl groups attached. Only carbon number 6 is a stereocenter. How do we look at the 4 groups around carbon number 6 if it's in a ring? The 4 groups on carbon number 6 are the nitrogen group, the implied hydrogen group, and the pathway around 1 to 5, and the pathway around 5 to 1. As we walk those 2 pathways, we get to that dimethyl carbon number 2 in different orders. We get there sooner with the carbon number 1 pathway than with the carbon number 5 pathway. So those paths are unique. The paths around the ring are unique, and therefore they are unique groups. And so carbon number 6 does have 4 unique groups attached to it. The 4 individual elements attached to carbon number 6 are the nitrogen, the implied hydrogen, carbon number 1, and carbon number 5. We can go ahead and say that nitrogen is the highest atomic number and will be priority number 1, and hydrogen will always be priority number 4. Carbon number 1 and carbon number 5 tie, so we play war. We go out to the next 3 elements immediately attached to those carbons. The next 3 elements immediately attached to carbon number 1 are carbon number 2 and 2 hydrogen. The next 3 elements immediately attached to carbon number 5 are carbon number 4 and 2 implied hydrogen. We're now ready to look for our first point of differentiation, but there is no differentiation. These groups also tie. So what do we do when we go out 1 carbon and those groups also tie? Well, it's just like that card game as a kid. When you would flip over that next card, if those would tie, then it would get really exciting because you'd have to put down 3 more new cards and flip over the next one, and you'd have to see the first point of differentiation. At that point, you would know who would win. So no big deal. We just draw a line and we move out to the next carbon in the chain until we find the first point of differentiation. We started with carbon number 6 and we looked at those elements, and carbon number 1 and 5 tied. So then we moved out to carbon number 1 and carbon number 5 and looked at those elements, but those also tie. So next we would go out to carbon number 2 and carbon number 4 and compare the next 3 elements attached to 2 and 4 and see if we can find the first point of differentiation. So we looked at the groups on carbon 6, the groups on carbon 1, now we're going to go out to the groups on carbon number 2. The next 3 elements immediately attached to carbon number 2 are carbon wedge, dash, and carbon number 3. We started with carbon number 6, moved out to carbon number 5, now we're out to carbon number 4. The next 3 elements immediately attached to carbon number 4 are carbon number 3 and 2 hydrogens. Now we found our first point of differentiation. We can compare the groups. The carbon is higher priority than hydrogen, so the carbon group, carbon number 1, will be the next highest priority, priority number 2, and the hydrogen carbon number 5 group will be the next highest priority after that, priority number 3. Had these also tied, no big deal. We would have just gone out next group and next group and next group, and if we had made it all the way around the molecule or all the way across the ring and we still hadn't found a differentiation point, then maybe that carbon wasn't a stereocenter to begin with. We're now ready to add our priority labels to our abstracted group. The nitrogen group on the wedge will be priority number 1. The carbon number 1 group off to the top right will be priority number 2. Carbon number 5 group down to the bottom will be priority number 3. And our implied hydrogen on the dash will be priority number 4. And if you're playing along at home, this is an R stereocenter. Let's bump it up one more ninja level for our last example. This last example is a tricky example to make sure you're really paying attention to the CIP rules. Go ahead, pause the video, see if you can find the stereocenters, and apply the priority labels to those groups. If you just try and glance at this molecule and assign the priority labels, you're likely going to get them wrong. But if you go through this analysis, the analysis is actually really straightforward. There's only the one stereocenter. I've abstracted it and I have our table ready. The 4 immediate elements attached to carbon number 2 are the nitrogen, carbon number 3, carbon number 1, and the implied hydrogen. Hydrogen will always be priority number 4, and nitrogen is the highest atomic number and will be priority number 1. Carbon 3 and carbon 1 tie, so we'll go out to the next 3 elements immediately attached to those carbons. Carbon number 3 is doubly bonded to this oxygen, so it's bonded to oxygen, oxygen again, and actually oxygen a 3rd time with the OH oxygen. Carbon number 1 is bonded to sulfur and 2 hydrogens. Putting those in priority order, we get the sulfur and the 2 hydrogens bonded to carbon number 1. We're now ready to do our analysis. The first point of differentiation is here between the oxygen and the sulfur. Sulfur is a higher atomic number than oxygen, so the carbon number 1 group is higher priority than the carbon number 3 group. Did you get that right? This is the one that everybody confuses. It is not the overall coolness of the group. We only need to look for the first point of differentiation. And when we line our elements up in priority order, the first point of differentiation says that this small little SH group is a higher priority than this much cooler looking carboxylic acid group. So while it may look odd on its surface, if we go through the analysis, it's really quite straightforward. Now we're ready to put our priority labels on our abstracted group. Nitrogen was highest priority on the top left. The carbon number 1 group on the dash was 2nd priority. The carbon number 3 group on the top right was 3rd priority, and the hydrogen on the wedge is the 4th priority. You can assign the priority labels to any stereocenter like a ninja.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.